Hello, welcome to this video. I assume most of you are going to be in Dr. Insco's class. If you are, this is week 5 Wednesday. If you're not in Dr. Insco's class, you have no idea what I'm talking about, then this is two-phase. Two-phase method is another way that you can solve problems that have greater than or equal to's or equal to's as constraints. So you can use two-phase or big M. The only benefit to two-phase really is that you might, if there's no feasible solution, you might come to that a little bit faster, that conclusion. But anyway, so let's take a look at this problem. Bevco manufactures an orange-flavored soft drink called Orange by combining orange soda and orange juice. Each ounce of orange soda contains 1/2 ounce of sugar and 1 milligram of vitamin C. Each ounce of orange juice contains 1/4 ounce of sugar and 3 milligrams of vitamin C. It costs Bevco 2 cents to produce an ounce of orange soda, 3 cents to produce an ounce of orange juice. Bevco's marketing department has decided that each 10-ounce bottle of orange must contain at least 20 milligrams of vitamin C and at most 4 ounces of sugar. Use linear programming to determine how Bevco can meet the marketing department's requirements at minimum cost. So for this problem, we're letting x1 be the number of ounces of orange soda and x2 be the number of ounces of orange juice. And then our objective function is the cost, so it's 2 cents per ounce of soda and 3 cents per ounce of juice. And we need to put in the coefficients for our constraints. So the sugar constraint, where x1 is soda, it's 1/2 ounce of sugar, and the juice is 1/4 ounce of sugar. So put those in there, and then we need to be greater than or equal to a total of 20 milligrams of vitamin C. So the soda x1 contributes 1 milligram, and the juice contributes 3 milligrams. And then, of course, the bottle needs to be 10 ounces. So it needs to be 10 ounces total between all the ounces. Okay, so then we need to add slack and excess variables where they go. So if it's a less than, you put a slack. If it's a greater than, you minus off an excess. And it's going to look like this. So that's our LP. And I like to keep, same thing Dr. Insco does, put the number of the S or the excess referring to the constraint. So S1 refers to constraint 1, E2 refers to constraint 2. And then anyway, for anything with an E or nothing, like this equal to down here, we need to add in some artificial variables. And now we're ready to start the method. So we have a new objective function. So you can either minimize the addition of the artificial variables or maximize the addition of the negative artificials. So we're going to minimize this one, and then you solve for 0, and then that's how we plug in these negative ones here. So and don't worry about the other one yet. Don't worry about the original objective function. And so now we need to justify these ones though. We need to make these pivots. So we need to get rid of these negative ones in the objective row. So in order to do that, you just do standard row operations, and the first few iterations are completed for us. So this one comes out like that, but we still need to get this one, so then it turns into this. So now that these ones are pivots, we're ready to go. We can start minimizing. So for a minimization problem, everything in the objective function or in the objective row needs to be 0 or negative. So clearly we gotta pick the most positive one. So it's going to be that 4. And then we do this, same as the maximization problem. We do ratio test between the right-hand side and the corresponding column and pick the smallest one. So 4 divided by 1/4 is 16. 20 divided by 3 is less than 10. 10 divided by 1 is 10, so we're going to pick that 3 to pivot on. And I actually just do this down here. So the row operations, in order to get this row, this 4 to be a 0, I multiplied this entire row by -4/3 and added it up. And anyway, so then there's the next iteration. And we still have a positive up here, a positive 2/3. and we conduct the ratio test. We see that 5 is the least, so you pick this 2/3 to pivot on, and this is the next iteration. And so now that the top row contains all zeros or negatives, this is the end of phase 1. So I'm going to come over here. Okay. So I'm just going to copy over that last tableau. And again, I wrote the original objective function. And so this is the tableau. So now that we're optimal, we can just eliminate both artificial variable columns. And this is because they are once phase 1 is optimal, you've removed all the everything is 0 or negative, you removed all the positives. If an artificial variable is a basic variable, meaning it's equal to something other than 0, then there's no feasible solution. But because these variables are both equal to 0, all the artificials, there is a feasible solution, and we can just eliminate this row and just swap in the original objective function solved for 0. So that looks like the iteration on the left. So you just got rid of those 2 rows and put in the z minus 2x1 minus 3x2 equals 0. But now again, first thing we need to do is to justify these. These need to be pivots. We need to make them pivot. So I did this one on the left first, standard row operations, and it looks like this. And then the next iteration is making this one be a pivot again. And there's that iteration. And now, because it's again a minimization, everything in the objective function row needs to be 0 or negative, and it already is. So after justifying the basic variables, we're already optimal. There's nothing else needed to be done here. So our optimal solution should be that, where x1 is 5, x2 is 5, z is of course 25, and actually I have z here and I have r up here. Whoops. And now we have slack of 1/4. Slack goes to 1/4, and E2 is 0. So we have to see if that makes sense. So we can plug these values into the original constraints and the objective function, and sure enough, 2 times 5 plus 3 times 5 is 10 plus 15 is 25. And then you plug in 5 and 5 here, and 2.5 plus 5/4 is 3.75, plus the slack of 1/4 is 4, and 5 plus 3 times 5 is 20. 5 plus 5 is 10, so it all makes sense, and this is probably the optimal solution. We can say with a good amount of confidence that this is probably the optimal solution. And we can go ahead and confirm that in Torah or some other linear programming solver. I know this video is going to be cut, so I'm just going to set it up really quick. I think you can see this. So objective function is 2x1 plus 3x1. We got the constraint of 0.5x1 plus 0.25 is less than or equal to 4. We have 1 plus 3 greater than or equal to 20. 1 and 1 equals 10. Let me just go to solve menu. And we'll do 2-phase. They might even cut off for you guys. I love watching this thing go. Okay, and sure enough, z, 25, x1, which is our soda, 5, x2 is 5. That's our slack variables, 1/4. So that's it. That's how you do 2-phase method. It's a replacement or a substitute for, or alternate for big M. You just use it for when you're solving any problems that have greater thans and equal to's or equal to's in the problem. And it's pretty much always going to start as a minimization, no matter what your real objective function is or your main one, because you're just going to jump straight into this. Sometimes this is equivalent, you do that too. And first thing you do is justify your artificial variables, and then you go ahead and run it like standard minimization, and then once you're optimal, swap in your original objective function and eliminate the columns corresponding to the artificial variables. And the other possibility is if an artificial variable, in this tableau here, once phase 1 is optimal, if an artificial variable is a basic variable, meaning it is a pivot column, but its value is 0, you can eliminate that entire row as well as the column. So once you've swapped in your original minimization, you've eliminated all the unnecessary rows and columns. In this case, there's only the 2 rows. You got to justify your basic variables again, and then in this case, there wasn't any need to continue, but at that point, you would just run it like a normal minimization, and in the standard simplex, and that's it. And then here we go. Hopefully this helped.